So it's my pleasure to introduce Thomas Wunschwiller. Okay, I tried. So he will be talking about a suitable tool for mitigating the risk of climate change with artificial intelligence, and this is going to be the findings on a white paper that was done between IBM, the University of Zurich, and the University of Applied Sciences. So welcome, and looking forward to hearing your talk.
Thank you very much, and welcome everybody. So maybe just first I have to say, okay, this is kind of the work from 50 collaborators from within Switzerland, academia, industry, government. So it's really a large crowd, and kind of we have also a booth just in the keynote hall. So Manuel from SATV is there, and here is also kind of the fact sheet. But I'd like to kind of inform you about the fact sheet, our findings. So the premise was like, hey, you know, we have all these great tools out there. Can we make a difference for climate change? You know, can we unfold kind of the research we perform kind of in this direction? So that's the goal. So basically, you know, we have this challenge, impact of the climate, but then also the businesses are challenged with the transition risks, you know, regulations, going towards net zero. On one hand, we have kind of then enabling key technologies. I'd like to discuss them. You know, tremendous progress. But then also, do we make use of those technologies? Maybe we have to use some of the key methodologies to make sure that kind of that technology transitions into the marketplace and makes a difference. And then, of course, we want to have beneficiaries from nature all the way kind of to the government and society, kind of to make Switzerland more sustainable. So this, as mentioned before, is the work, the hard work, 1 year, summed up kind of in the fact sheet and the white paper study from 50 academics, government people, and industry partners. So first, the issue. We see here data from Meteo Swiss, temperature drifts from pre-industrial times all the way to today, and we see for Switzerland. So we see already a 2.5 Kelvin increase in temperature. Okay, maybe hard to believe today, but climate is statistics and not just the weather of today. So that's what you observe in the Paris Agreement. The hope was kind of that as humankind we could manage with 1.5 Kelvin temperature increase. But climate is complex, so in Switzerland we are already beyond kind of that target. Worldwide, I mean, the numbers are in the range of 1.5, I think, to 2 Kelvin, I believe. But, you know, different regions will face different issues. But there's definitely change, and the change is rapid. So what does it mean? I mean, temperature, okay, what does that mean for me or for you? So we see, for instance, heat waves. We have seen droughts kind of in the western part of Switzerland. We see that the kind of the 0 degree line goes up, you know, ski resorts, sorry, you have to rethink. But then also we have less snow days. So this is a big problem also for electricity production, kind of hydro power plants. And also we have increased heavy precipitations with also higher frequency. So everybody of us is affected in one way or another. And so we should spend some of our neurons, and maybe also the neurons of artificial intelligence, to tackle that problem. But okay, look at also what is actually risk, right? On one hand, we have here the climate disaster risk. So basically, we have the weather and climate events on one hand. You know, some of the weather extremes are caused by anthropogenic emissions, greenhouse gas emissions into the atmosphere. The atmosphere is warming. There's more energy in the atmosphere, there's more of these extreme events. But then if there's an extreme event and nothing is there, okay, I mean, who cares, right? So, so which direction? Okay, good. So the question is then also exposure. Is critical infrastructure in the area where these extreme events occur? So that's a question you have to ask yourself, maybe also supply chains. You know, not only the weather in Switzerland matters, but like our industry is very, and also kind of our supply chain and retail markets are very international. And then the question is like, how vulnerable are those assets to those exposures? So that kind of is then the climate disaster risk. On the other hand, as an industry, I mean, luckily, kind of the public or society woke up and identified climate change as a big topic, trying to mitigate climate change. So there's kind of this movement kind of to reduce greenhouse gas emissions, hopefully. So also from, let's say, in the European Union, the European Green Deal, for instance. So there's kind of that part, but then also companies are being regulated, so they have to come up with ESG reports, they have to report on greenhouse gas emissions, they have to report on their net zero emission strategy, etc. And that's kind of what we call the transition risks. So there's legal and economical requirements. So it can be quite tricky, as we've seen before with AI regulations. This is another regulation. So, I mean, there's a zoo out of regulations there, and the question is also there, could AI help kind of to simplify, kind of to deal with these regulations? Not to do greenwashing, by no means, but just like to perform and implement kind of those regulations more meaningful and better. And again, okay, if you go back, so we have kind of also there kind of the exposure. It's kind of like could be your production, it could be your supply chain, etc. And how vulnerable are you kind of to kind of comply with kind of these regulations. So now, key technologies. What do we have there at hand kind of to make a difference? On one hand, with kind of increasing temperature, oh, okay, that jumps. All right, okay. So with increasing temperature, we also see, it's just a correlation, it's not causal. We also see more and more satellites in space. So, and here the interesting piece is kind of the following. I mean, you all know Google Maps, and then there's very high resolution data. You can see cars, etc., but it's static. But the world is a movie. I think. Oh, okay, it looks a bit static right now. But okay, the world is dynamic, and so basically, kind of the important piece especially in environmental science, is kind of how often do you make observations with satellites? And nowadays we have, like, on a daily basis, we get information from space, from any location on the planet. So we have, for instance, open data from ESA and NASA in the range 10-meter resolution. You get it maybe every 2 or 3 days for Switzerland. The world is mapped, right? It's for free. So kind of the color code means the dark code are more expensive. So this is free. Then there's some commercial satellites out there. They have resolutions down to 30 centimeter, and they, may track kind of events on a daily or even more frequent basis. Okay, this jumps a bit. All right, so there's a lot of data, and just by the way, it's roughly 800 petabytes of data. So big data guys in here, kind of, they know that may be a challenge to deal with. All right, on the other hand, AI. What do we see in the AI world? Okay, everybody has had his or her own ChatGPT moment when trying out the LLMs. But the same thing happened last year also in the weather forecasting world. And that was pretty amazing. So I just came back from the AI for Good conference in Geneva from yesterday, and there were like weather scientists discussing kind of with the AI scientists, if what are these models really worth? And the amazing thing is, like, the European Weather Forecasting Service, which is kind of the top standard on the world, kind of admits that kind of these AI models are on par with kind of the physics-based models. So far, kind of to model kind of precipitation around the planet or temperature, we used kind of these physics-based models, solving partial differential equations. And so that's kind of the red line here. So that indicates kind of forecast per day, like up to 10 days, what the error is. So the lower, the better. And then all the other plots or lines are AI-based emulators. So they were trained on the rich data set from the red curve. So basically kind of it's a reanalysis data set, but okay, it's a kind of weather data from those institutions. Organizations took that data and trained AI models, and they have the similar skills to do forecasting up to 10 days. And the amazing thing is, at 4 orders of magnitude less compute once the model is trained. So you can now do a forecast on your laptop compared to a supercomputer. So this is a big change. So that's just the beginning there. So the question is, can you use this also for climate models, which span more than 10 days, obviously, like more like decades and so on. Okay, an example also how you could use this in kind of an example of flood risk estimation. We have satellite observations, geospatial data, satellites. We can, during an event or after an event, for instance of a flood, we can map out kind of the extent of the water. So this would be here, like with computer vision approaches, kind of using semantic segmentation. We can go further and also look at buildings before and after the event, and can identify the damaged buildings. So then we know kind of for a certain weather hazard variable, we have a certain amount of damages for a specific infrastructure, and that's kind of what then results in impact functions, kind of a description of the risk of a specific assets for a specific event. But then we want to look into the future as well. So then we need kind of these AI weather generators, which produce extreme events. We can feed that, for instance, precipitation together with soil, land use, and elevation maps into, again, a physics-based model to identify kind of flood risk maps in the future. So if we know kind of the flood risk, we combine it with these impact functions, kind of these observations from the past. We can then identify, for instance, with OpenStreetMap, where we have assets, what the risk is and the damage potential kind of these extreme events. So that's an example. You can see everywhere some AI models to be deployed here. Okay, so what? So looks like we solved the issue, or we just can execute with the AI and make a big difference. But unfortunately, kind of we see that the current situation is that the pickup is tricky. So I'm talking about big data. So yes, data is freely available, but okay, 800 petabytes of data. Okay, it's a challenge. Then compute resources. Everybody's fighting for GPUs. Okay, so what do we do? I mean, okay, we wait another decade. And then also we see kind of AI algorithms and workflows. I mean, quite often here in this domain, we have interdisciplinary teams, or we have to work together with interdisciplinary teams. But quite often we see also that people come from the research. Let's say people in research, they have projects, maybe a PhD, one person focusing on a climate problem, and typically they come from the environmental science side. And they are very good on their kind of topic, but they may not kind of be knowledgeable about maybe the computer science methodologies some of you in here in the room would know. So and then the problem is like this code is typically then not scalable, or maybe just the funding is not there kind of to transition it to the public, or just like to continue with that code. So what we want to foster is kind of that we kind of the objective is kind of to have like better overlap between these disciplines, kind of provide open data with one click, kind of provide GPU access and scalable code. So luckily, okay, so the ALP system is being installed, and I mean, it's amazing. I mean, okay, I mean, it's always amazing kind of when it's on the top 500 list, it's number 6 worldwide. Okay, that's super cool. And also what's super cool is kind of that there should be access kind of to industry and other partners from outside of academia kind of to those machines. Sure, Meteo Swiss is already there, ETH is there, but there's other stakeholders which can make a difference in climate change. On the other hand, to kind of deal with the data, so we hope kind of that the community is continuing pushing kind of standards, like for instance, OpenEO is kind of a platform, kind of or an API, which allows you kind of to have access to geospatial data with the same API interface, while the backend could be very proprietary or different, kind of for different organizations. Kind of maybe ESA would provide such an interface, Amazon would provide such an interface, and then kind of data exploration would be much easier. So kind of a harmonized, kind of at least API access, but the backend can be very much different. Or then with kind of this geospatial data, the problem is like, okay, you may want to satellites, they are like orbiting in North and South Pole kind of orbits, and kind of over time they map out the world, but there's a lot of missing data, and just to find kind of those data sets is hard, and so that's kind of where some tools like spatiotemporal data catalogs come in, which kind of on a polygon map out where data is available. So kind of also just to find data in 800 petabytes of data is like it's really tricky. So, but at least kind of some of these tools are emerging. In addition, we see also, I mean, everybody's talking about these foundation models, and I think they also can have a difference or make a difference in kind of in this world. So basically, together with NASA and also ESA at IBM, we work on these foundation models for Earth observation. So the concept is the following. I mean, NASA said, you know, we had like all this data, and then we have the scientists, and then they would perform a flood model for the US. And then there's a flood in India, but okay, then you know, it's out of distribution, and okay, it doesn't work. But annotation is still difficult. So we have a lot of data, but you know, you have to map out kind of the flood to do the segmentation. So yeah, it's hard. So that's basically kind of where this foundation model concept comes in handy, where you do a pre-training task on self-supervision. So basically, you can sample data from the entire globe. So to have a diverse and rich data set, you train an encoder-decoder model, and then you just use the encoder and perform a supervised learning task with few annotations. And that's kind of how you can get then to a model which generalizes better across the planet. So the problem, they had like a model zoo of individual models, okay, maybe in this region, in that region, and so on. And in this case, kind of we have the chance kind of to generalize much better across the planet for different downstream applications. So let's get to also methodologies. I touched a bit on those kind of before. So without kind of those methodologies, the key technologies, they won't make it kind of to the marketplace, or won't make a big difference. They would maybe be stuck in kind of the research domain. So basically, one thing I think, exactly as mentioned before, you know, quite often environmental scientists are working on those problems. But this really has to happen in concert with kind of computer scientists, because, I mean, we're talking big data, we're talking about compute clusters, and also the code has to be reusable. So we really want to make sure that kind of, you know, for scalability, kind of the versioning, containerization, and all these kind of best practices are used, and then kind of isolation of kind of the code base into different containers. Then also kind of adhere to the open science principles. Think about, I mean, data has to be findable. I just showed you before kind of an example how to do that. But then also these communities are extremely powerful, as for instance, OpenStreetMap shows you. So that's really the strength there. In addition, don't forget responsible and trustworthy AI. I mean, we heard it before, but also here in the context, let's say on these large models, if I touched on foundation models, I should be careful, because the training needs a lot of energy, may release a lot of greenhouse gas emissions. So we have to be extremely careful kind of to make sure that kind of also the AI model efficiency is a consideration. But then also, like from the application side, that inclusivity is important. So, you know, quite often kind of we have like the let's say the global south, they don't have these data pipelines to consume these petabytes of data. So we have to think about how can we make sure that also the global south can benefit from these technologies, where the impacts may be larger even than in the north. But besides kind of resulting in a more sustainable society, we should also keep in mind, hey, there's some opportunities out there, you know, like there's some sustainability opportunities out there. Here exemplified by just like this chart showing kind of the Swiss green fintech startups as one example, right? I mean, there's many more examples where you have opportunities where you can show, hey, you know, like that's the way you have to do it. That's the way you can have an impact, and then there's also value. So we shouldn't forget about this. So in this, in the white paper and also in this fact sheet, we have some additional case studies also, kind of to demonstrate kind of how AI can make a difference. For instance, in urban heat island prediction, above ground biomass. So this is carbon market related, kind of how much biomass is there, deforestation, reforestation, releases of greenhouse gas emissions observed from and identified by AI, but also kind of how to improve the efficiency of your process in the carbon footprinting. Let's say if you're a retailer and you're Migros and you have to identify how much carbon each of the products kind of emits. That's a challenge, you know, if you have to do this to this very single screw on each component. So here also AI can help you to improve and make this process more efficient. So in summary, we have some recommendations for decision makers. So hope some decision makers are here. And on one hand, it's kind of build capacity for Swiss sectors, kind of really make sure that we have national competence centers connecting AI and the sustainability world, ensure access to international programs. So we heard like Horizon Europe, we are not really associated. Copernicus was also rejected recently, and so on. Destination Earth, we are not part of. On the other hand, kind of implementation of principles of open science. So we see there's some progress with the EMBAG legislation being implemented. And then, very important, let's work together, like software engineers and climate scientists, as mentioned before. As a fifth kind of recommendation, accelerate the translation of the research into the marketplace. So this is important. So here we really like to pick your brain. So thinking about private-public partnerships, you know, can we do something together, like industry, bringing some funding, matching funding from the government, and then kind of have a much higher, larger impact from those research results. Please keep in mind responsible AI and also kind of including kind of fostering kind of the quantitative understanding of the climate impact to us all and to your organization. We also have some recommendations for the data scientists. Okay, I mentioned it before, like fair principles, like make sure that your data can be accessed and adopt these standards. So it makes it easier for everybody to work with. Sustainable applications, kind of federation principles to consider. You know, we share data. Reusable, apply data code and modeling versioning principles and state-of-the-art software architectures, and then kind of the responsible AI and machine learning concepts. So with this, I'd really like to thank, so I will start reading now. Sorry, yeah, forget about it. Okay, so thanks a lot. So there's the booth over there, kind of SRTV, fact sheets and so on. Yeah, and would be cool kind of to chat about how could we kind of bridge kind of this, code from research into opportunities on the marketplace and make just like a more resilient Switzerland and society overall. Thanks.
Thank you very much. Thank you, Tom. Questions? Okay, we have a lot. Let's start with you.
Thank you very much for your talk. Just one question. Do you see opportunities for this influencing policy? Because right now, climate policy relies a lot on like impact assessment models. I mean, and they are controversial to say the least. If you think about Nordhaus or anything like that. So, do you see opportunities for this also to go beyond just like marketplace action, and like have a policy impact?
Right, I think on one hand we have kind of the International Panel of Climate Change kind of reporting on the research findings, so extremely important, right? Politically not biased, hopefully as much as possible, not. But like as a guidance kind of then for the politicians kind of to act on. Luckily we also have society kind of who woke up and kind of the consumer pressure. And kind of with this initiative also we try to have an impact kind of. We see a lot of research going, but you know, at the end of the day, you know, how much really, you know, how much do we really change kind of then the marketplace or society with kind of those solutions? Does that? Yeah, maybe we can discuss. Okay, yeah, okay.
Please.
Thank you. Very interesting, especially the sustainable AI topic. I think it doesn't get enough coverage. Normally, is any concrete initiative like really to look at the benefit of training a new AI model versus the energy it uses? Is there anything you could mention there?
Yeah, absolutely. So we run a EU project called Embed to Scale. So where also we think about, I mean, first kind of assessing kind of the entire kind of chain of model training, data transfer, and so on, and then also inferencing kind of on this data. This data is a bit different. Like if you have LLM requests, this is in the billions of API calls. So here it's more about the data volume is large. But then what we think to do is also kind of, typically we are used to look at images, but like to get insights from these applications, you are interested in the insights and not in the image itself. So basically what we want to do, we want to use the foundation model to generate embeddings, and those embeddings being compressed representations. So let's say ESA would kind of gather satellite data, you would run it through an encoder of a foundation model, and then you would only share the embedding, which hopefully is like a 100x kind of compressed form, but still providing the utility. So you would only have to do it once. So you do the compute once, and then there's less traffic, less storage, and also for the organization which does inference, kind of they can use a fairly simple decoder head. So there's some ideas out there, but we have to materialize. Yeah, okay.
One last quick question.
Yeah, thanks. So I feel there's always a bit of a misunderstanding between energy consumption and CO2 footprint. But my very quick question is, the new supercomputer, the ALPS, it consumes quite a lot of energy. Is this green energy, or is it also sourced from maybe coal or other things? Because that's what really makes a difference.
Yeah, I mean, the only thing I could say, I mean, I'm not operating ALPS, point one. Point two is, I guess, that's kind of the standard, probably Swiss grid energy mix. I don't know. Maybe they have a specific, somebody, I mean, exactly. So somebody from from the supercomputing center would probably have to tell. Somebody knows? It's hydro?
It's 100% renewable.
Okay, it's 100%. Okay, then it's 100. But you know, I mean, somebody had to produce the system, right? So kind of the kind of just the, sorry, that part also has to be put into the equation, right?
Also, if it's being used for that, it's not being used for something else. You know, we can also look at it like this. So, it's good?
Yeah.
Anything else? So I think we thank the speaker again. Thank you for this excellent talk.
Thanks.
Thank you very much for coming to
thanks.
STS.